Thanks for sticking around till the end. I'm Dhruv Balwada, and this is some work I've been doing with Schaefer Smith and Ryan Abernathey at New York University in Columbia. So, and as the title says, that what we are interested in is measuring the transport that's driven by eddies. But first, let's try to understand what I mean by measuring. Like, what context is the measurement going to be made in? So, in coarse resolution ocean models, there's usually two parameterizations that go in for mesoscale eddies. One that represents the eddy-induced advection, which is associated with the adiabatic isopycnal slumping and acting as a sink of available potential energy. And this is represented by the Gent and McWilliams. And the way this appears in the buoyancy equation is as an antisymmetric GM tensor, which also represents an eddy-induced velocity. One thing that's interesting to note over here is that when you apply this parameterization to the buoyancy equation, it looks very similar to what you would get if you did transformed Euler and mean. So there's no symmetric part. And the QB that I have on the right side is just forcing at the surface and small-scale diapycnal effect. The other parameterization that goes in is for isopycnal stirring. So this doesn't change your available potential energy, but what it does is that it mixes tracers apart from buoyancy, so things like oxygen or chlorophyll or things like that, along isopycnal surfaces. And this is usually represented as a symmetric tensor, and it appears in the tracer equation for the large-scale model as this term on the right-hand side, which is the symmetric tensor. Note that the GM-driven eddy velocity still sticks around. So for tracers apart from buoyancy, there is eddy-induced advection, plus there is eddy-induced stirring. The final note that I want to make about what coarse resolution models usually do is that the GM tensor has this one scalar sitting outside, KGM, which is assumed to be constant, or at least it's isotropic. There is no directional dependence. And the same thing is assumed for the symmetric part, the Solomon-Reddy part. And also, usually the assumption is made that the GM diffusivity and the Reddy diffusivity are the same. So what is our goal? Our goal is to diagnose the influence of mesoscale eddies in a 3D ocean model under the framework of this mixing tensor. So, kind of going back to Greg's talk, I think the structure of the model that we are assuming over here is this mixing tensor model. So the model that we use is this model that's become quite popular now. It's a channel model. It has, it's forced by a linear temperature restoration at the surface, very simple wind stress. There's a sponge layer in the north to maintain the interior stratification. And we also introduced a meridional ridge that breaks the zonal symmetry. So there is less eddy activity in the upstream direction than in the downstream direction that you see over here. And this is what we want to diagnose. So we have, for any tracer, we have the fluxes on the left-hand side, the U prime, C primes, and we assume that they are related to the large-scale concentration gradients through this tensor. When you make this assumption, one really important thing that happens is that you kind of separate out the effect of the eddies from the tracer. So you can put in any tracer that you want. It's the same diffusivity tensor that acts on all of them. So in a sense, this model is just flow dependent and not a function of the tracer. And so this is the method that we use. It's called we call it the multitracer method, and it was first used by Plum and Malman in 1987, and most recently by Bachman et al. In 2015, who have used it in a more ocean-like setup and kind of ironed out a lot of the wrinkles that were there. So what you basically do is that you, so on the far left over here, what you see is that you try to restore some tracer profiles. So over here, I'm just showing two examples. One case where there's a tracer profile that's restored only in the x direction, so it's sort of a sinusoidal mode 1 wave. Another one is a linear tracer profile that's restored only in the y direction. You let it evolve with the flow and reach a steady state, and at which you see these thin contour lines. That's the kind of the mean tracer profile that emerges when you restore to the profiles that are shown in the color. So now once you have these mean profiles, you can calculate they're mean gradients, and I'm just showing the gradients in a single direction. So for the X tracer, the gradient in the X direction. For the Y tracer, the gradient in the Y direction. The point being that you do end up with a decent amount of gradients, and so the gradients are not going to zero. And then these are the diagnosed tracer fluxes in the respective directions for these two tracers. Now what you do is that you take your mean tracer profiles, you take your eddy fluxes, and just put them in this equation, which is that you do a least squares fit to estimate a diffusivity tensor. And then what we do is that we take this diffusivity tensor and see how well they actually end up reproducing these tensors, because you're doing a least squares fit, so it's entirely, using a least squares fit, it's entirely possible to fit a line through a circle. And that's what we wanted to check, if it was a circle that we were fitting through a line or it looked something like a line. And what you see over here is that the tracer fluxes that we reproduce from the diagnosed tensor look extremely similar to the tracer fluxes that were put in. So that means that it's doing a good job. One thing that I want to note at this point is that all the previous studies that are in the published literature, nobody has ever seemed to apply this method in 3D. I know that Scott's doing some work on this right now, but it's a little bit surprising that this method's been around for over 30 years and nobody ever used it in 3D, and I don't understand why. But going on, so that was tracers that we actually fit to estimate our kappa. Now you can ask the question of if we have actually recovered a tracer-independent kappa. And so what we do is that we try to check another tracer. So buoyancy was not involved in the inversion process. So we ask the question of how well do you do with buoyancy fluxes? So in the top row, we get the flux of buoyancy. On the left, this is the true flux. This is the reconstructed flux. They look extremely similar, so that's a good thing. Not only is it the flux that looks similar, when we calculate the flux divergence, even that looks really good, which is very surprising. In a good way. So now that we have the buoyancy fluxes and we have this tracer, we can ask a few questions. What does this tracer look like? So we can break this tracer up into a symmetric part and an antisymmetric part. And on this slide, I'm showing you what the properties of the symmetric tensor are. So the symmetric tensor can be broken up into 3 eigenvalues. They are shown over here. So there's lambda 1, which is the largest one. You see that there's large values in the downstream direction. The little green lines show you the eigenvector that's associated with this eigenvalue in the horizontal direction, and it's more or less aligned with the mean flow. The second plot shows you lambda 2, which is the second largest eigenvalue. Again, it's large in the downstream direction, and the eigenvectors associated with it are oriented perpendicular to the mean flow. And then this is lambda 3. It has some positive and negative values, but it's orders of magnitude smaller than the 2 other eigenvalues. And what I'm showing over here are just 2 maps, two kind of joint PDFs of the lambda 1 eigenvalue as a function of the eddy kinetic energy, and you see that there's a relationship as you would expect, and this is for lambda 2. Again, there's a relationship. It's kind of interesting thing that you note over here is that it kind of seems to bifurcate into these 2 sets, and I don't show it over here, but the lower values are actually the values that are closer to the surface, or kind of around 300 or to 700 meters, indicating that there might be some mixing length suppression going on for this. So then we can look at the properties of the antisymmetric tensor, which has these psi 1, 2, 3 stream functions associated with it, and an associated velocity. So for example, psi 1 over here corresponds to a flow in the YZ plane. Psi 3 corresponds to a flow in XY plane. It's a bit hard to visualize these, so over here I'm just going to show you what the zonal averages look like. So this is a plot of the zonal averages. So the first one is just the mean velocity. And because we don't have any ridge above 2,000 meters, there's no blocking, the mean velocity goes to almost 0. This is the component that we get from psi 1, and this is what in this model drives all the residual circulation. And the final interesting thing that we note is that below the ridge, where psi 3 enters the eddy-driven velocity as the x derivative, you get this northward velocity, which is trying to cancel out the southward velocity. And I think this has to do with some sort of eddy-induced velocity canceling out the mean velocity in the gyres that form below the depth of the ridge. So, and this is a Jensen-Williams estimate of diffusivity that we obtained out of this model. One thing to note is that this has values on the order of a few hundred, and the values that I showed you for the eigenvalues of the symmetric tensor, they were on the order of something like 5,000. So the GM-induced diffusivity is almost an order of magnitude smaller. So now you can ask some, try to figure out if what we have got is exactly what we wanted, kind of things. So some subtleties. So what is the role that S and A play for buoyancy? Now, when we started out, we wanted to estimate a symmetric and antisymmetric tensor that is similar to what we want to put in a coarse resolution model. Now, one of the assumptions that's made in that case, because you transform your buoyancy equation in this TEM framework, is that the antisymmetric tensor encompasses the entire influence of the mesoscale eddies on buoyancy. And what we find over here is that if you look at the flux only in a zonally average sense in this model, and only in the place where there is no ridge, so the top 2,000 meters, this is the total meridional heat flux. Below the mixed layer, there is no contribution from the symmetric tensor. All the contribution is from the antisymmetric tensor. So this is an indication that the antisymmetric tensor that you get is giving you something like the GM tensor. And so you can use this to directly get GM. But now if you go to 3D, you don't find this anymore. What you find is that the contribution that you get to the heat flux from the symmetric tensor and the contribution that you get to the heat flux from the antisymmetric tensor are, they're incomparable in magnitude, and there are regions where they sometimes cancel each other out, sometimes they add up to each other. And the same thing happens for the flux divergence, because a lot of people might look at this and they're like, oh, there's a symmetric tensor that's involved. It's probably all rotational fluxes. You take the divergence, it all goes out. It doesn't. When you look at the flux divergence, you get the same thing. The symmetric tensor plays, the diagnosed symmetric tensor plays an important role. So what this suggests is that generally the symmetric tensor that you get with this method is not the Solomon-Reddy symmetric tensor, and the A is not the Jenner-McWilliams, but the differences might be small. And then you can ask the question that why is S interacting so strongly with buoyancy in the interior in the 3D case? And I'm just going to show you a little schematic of why I think that might be happening. This question has not been completely answered, but this is the 2D case, and this is just what we find is that there is a large eigenvalue lambda 2 that has its mixing direction that's oriented with isopycnals, and then there is a lambda 3, which is the small eigenvalue that's oriented perpendicular to the buoyancy contours. And so when you multiply S grad B, you get a small buoyancy flux, which is not exactly diapycnal, but it's quite small. When you go to 3D, and if you look at a point only in a plane, this mixing tensor eigenvalues get rotated. And so now you have lambda 3 that's still acting mostly across your isopycnals, but lambda 2 has slightly turned. And just because lambda 2 is so much bigger than lambda 3, you end up getting a significant contribution of the symmetric tensor on buoyancy. And so you can try to understand this vaguely from the variance transport equation or the variance budget. And so this is on the top, I've just noted down what the variance budget looks like, where there is the transient term. In our model, everything was run up to stationary steady state, so this went to 0. There's some transport. There's the production of variance. There's the dissipation of variance by the molecular or numerical dissipation. And when you do a zonal plus time average, there is no meridional flow in this model, and so there won't be any variance transport in the meridional direction. And so S grad B dot grad B, at least the projection of the flux due to the symmetric tensor on the buoyancy, because there's 2, is almost 0, which suggests that S grad B might be small. This just suggests that. But when you take a time average, this thing balances the variance transport term, which suggests that there's going to be at least some largish contribution in S grad B. But this is not the complete story, because I don't have time to get into it, but you can talk to me later, is that S is this full tensor with its eigenvalues and eigenvectors, and you can't just look at one variance transport equation to explain what's going on, but it just gives you, it's just suggestive. So in summary, we diagnosed a working mixing tensor that works in 3D, and by works we mean it reproduces the fluxes and flux divergences. The eigenvalues of symmetric tensor are anisotropic. A GM diffusivity that comes out of it is smaller than the Solomon-Reddy diffusivity. Both A and S contribute to reconstructing the buoyancy fluxes in 3D. And contribution due to S on buoyancy is non-negligible, and this is probably due to variance transport. I'm not implying that we need a new parameterization in 3D to parameterize the symmetric tensor. All that I'm saying is that this diagnosis method, you need to think about it a little bit more deeply. Thank you.